All right, so we'll get started again. So our next talk is how to not break SIDH.
Indeed.
Tell a story first.
What's the story? You go ahead.
That's what Nikki did, right?
Oh yeah, the story. So we tried to break this and then we couldn't. So it's basically the summary.
And we couldn't in lots and lots of different ways.
Right. So the basic story is, so I'm Lorenz, this is Chloe, obviously, if you couldn't guess by the genders of people. I did my review of PhD now, and one of the first things I did when I started was look at this protocol and try to figure out how to break it. And together with Chloe, who was a postdoc in Eindhoven. And
you can blame everything on me.
yeah, also Tanya is involved in this whole thing, sort of in many different ways and times.
I made you feel great.
She tried to make us break it, but we couldn't, so sorry. Right, so probably for the biggest part of the audience, SIDH is not a thing, so this talk is not only split in half according to the presenting people, but also according to the topic, which is, well, the first half is basically an introduction to isogeny-based crypto, which is another thing we're going to explain. And the second half consists of a list of all the different failing or not obviously working ways to look at this problem and not break it. Right, so what is this all about? This introduction starts from a thing that I guess everybody here knows because you're all familiar with us. So if you just think about Diffie-Hellman, the normal Diffie-Hellman protocol that was presented in the 70s, it works in a finite group. You start with some generating element. Ideally, it has a big prime order, else it's insecure. And then Alice and Bob do this thing where everybody computes G to the A, and or G to the A and G to the B. They swap their elements and raise it to the same secure exponent again. And well, because this exponentiation operation is commutative, they get the same secret. And if discrete logarithms and the Diffie-Hellman problem are hard, then well, nobody along the way can figure out what the shared secret is. But now the problem is, as we learned yesterday, it's broken. There should actually be a little footnote here, it's not classically broken. But, at least for quantum computers, this is broken in every case, because Shor's algorithm solves this problem in all groups. This is actually one of our biggest research topics in Eindhoven, post-quantum crypto, For us, it's broken. So you need something else, right? For example, you can think about, well, the only thing I really need is like a commutative operation, right? So you can think about, what if I do a graph walking Diffie-Hellman thing, where the operation is not exponentiation, but I'm looking at a graph that has some nice structure, like this map of Manhattan, and I start walking. And, well, as you can see here, since this is very rectangular, you can walk around in a very determined, regular way. And now everybody just takes their own secret path that they determined beforehand and appends it to the endpoint of the other party. And, well, because this grid of streets is very nice and rectangular, they end up at the same point, which is somewhere in Central Park, I guess. That's not actually part of the grid, but, whatever.
Graphing failure.
Actually, there are many more. So first of all, this took forever to make because the streets are not actually that regular. So you have to adjust it a little bit. So to be quite honest, the paths are not actually the same. It's close, but not quite right. So yeah, I'm blaming the city planners of Manhattan hundreds of years ago. So in this example, the problem is it's not actually secure, right? If you look at the map and you see the start and end points, it's very easy to figure out paths. You just count the number of streets and you walk that way, and you're done. So we need something else. And that's where isogenies enter the picture. So on a very high level cryptographic complexity theoretic view, an isogeny is, or an isogeny graph is basically a source of exponentially sized graphs. I'm going to say what isogenies are in a minute, don't worry about it now, it's a thing. And just like in Manhattan, we can walk around efficiently on these graphs, which is of course very useful if you want to walk on the graphs, right? We should have some algorithms to do this in a not taking forever way. And you can argue mathematically that on these graphs, it's like for all pairs of nodes, there exists kind of short paths, which is also good for crypto, right? Because you want to have your random walks mixed kind of quickly. And contrary to the Manhattan example, there are no known algorithms that give you a path when you just plug in the two endpoints. And well, no efficient means different things depending on exact context, but in any case, there's definitely no known polynomial time algorithm. Right. And the last thing we want for crypto is that there should still be some sort of structure that makes the Diffie-Hellman key exchange work. Right? So it's easy to come up with an exponentially sized random graph, but then if you just walk in some way and you try to concatenate those two paths, you're going to end up at a random node, and Alice and Bob just get to two different random things, and they're screwed. So we still need some sort of structure, but the structure shouldn't be so obvious that it's easy to find a path. Right, I just said this. And that's basically what the very big high-level picture thing that isogenies give us. It's a big graph that's efficient to navigate on and has enough structure to make the Diffie-Hellman key exchange work, but not enough to be broken. Right, so I just promised I was going to tell you what isogenies are. So here's a 5-slide introduction to all the math in isogeny-based crypto, where I still try to strip away most of the things that like. There's lots of details under the rock, but. Right, so if you have any questions, just interrupt me and ask. Right, first math slide, elliptic curves. This graph has nodes and edges, right? And the nodes are elliptic curves in some sense, like they could be isomorphic sets of curves. But just think about curves. So each node is a curve, and then the edges are going to be the next slide. An elliptic curve is given by an equation like this. If you've never seen it before, don't worry about it. It's an equation of a specific form. And yeah, I mean, you can look at solutions of these equations, and that's an elliptic curve. The interesting thing is, and the reason why cryptographers mostly care about elliptic curves, is that the solutions to this equation, the points on the curve form an abelian group. So you can add and subtract them, and there's formulas to do this. I guess also most people have seen this before don't remember the formulas. They're not extremely intuitive. There's a nice geometric explanation, but we don't care about that. It's just like a group, you know. Just think about Z mod n, but with a nice representation that doesn't make it obvious what the elements are. Right, second math slide. We now have dots, right? So to make the graph, we need to fill in some lines. And, well, as a mathematician, once you have an object that's somehow well behaved, you also want to study the kind of maps between these objects. And an isogeny is really just the natural notion of a map between two elliptic curves, meaning that it's given by rational functions, which is in line with the fact that we're looking at algebraic curves, right? They're given by equations of polynomials. And so the maps between them should be restricted to rational maps, meaning fractions of polynomials. And, well, I also said that elliptic curves carry a group structure, so we also wanted to require that these maps are group homomorphisms. Every group homomorphism has a kernel, and we just call the size of the kernel in most cases. So this little asterisk means it's a technical thing, don't worry about it. All the isogenies we're going to see are separable, more or less. Not going to be an issue. Right. So we basically want to, like, there's different sized isogenies in some sense, right? And the size is the number of points that it maps to the point at infinity. For example, in every abelian group, any group actually, you can look at the map that raises an element to its mth power for any n, just integers. So, right, clearly you can take any scalar, you just multiply a point by itself so many times. And as it turns out, for the curves, the degree of this map is m squared, meaning it kills m squared points. And also by the curve theory, we know that the kernel, well, I don't have a pointer, looks like a product of two copies of Z mod m. So it's just two cyclic groups together. It's like a two-dimensional. You can think about a torus, really. I guess. Second example, so this was a very specific example, right? It's a map from a curve to itself. It's given just by scalar multiplication. You can actually have the scalar multiplication in any group, so this is not specific to elliptic curves at all. This one is a bit more special. So here we're really doing something with the coordinates of the points, right? We're not just using group structures of black box, but we look at what are these points really, and we apply specific algebraic operations to them. And yeah, if you plug this into the equation, you're going to see that this works out. And we actually map a point from the first curve to the second curve. And also by looking at the equation for this map, you can see that this doesn't actually take any points that is not already infinity to the extra point of the neutral element. So this is actually an isomorphism, and the kernel is just a trivial group. Last example, this is a more really typical isogeny that's just like a random looking isogeny between two curves. It has degree 3 because if you look at the denominators of this equation, this still doesn't work obviously. You can figure out that the only points that actually have 0 in the denominators here are this, well, the 2 points with x coordinate 2 and the additional point that's always mapped to infinity. Right. So these examples are kind of representative of different classes of isogenies. Well, we had a scalar multiplication, we had an isomorphism, and we just had a typical degree 3 separable isogeny that takes points to other points. And we like to give these things names, right? So an isomorphism is just an isogeny from a curve to itself, and then for technical reasons you also include the zero map. And now since you have a map from a curve to itself, you can also compose these things and you still get a map from the curve to itself, right? So you have composition as an operation, and you can also add these things just because you can add any two homomorphisms between groups. Which means that the set of anamorphisms forms a ring, which is the reason why we included the zero map. And this plays a big role in the theory of elliptic curves. And the other thing that's not true for all group homomorphisms in all categories is that associated to each isogeny, you get an isogeny back in the opposite direction that satisfies this nice property that when you compose the two, you get a scalar multiplication. So in a sense, this is a bit like an inverse, except that you're not getting the identity map when you compose them, but you get a scalar multiplication by the degree. Right. Third math slide. I'm sorry for all the math, by the way. We can't do without it. So we want to do all of this on a computer somehow, right? That means we should be able to bound the sizes of the things we're interested in. There shouldn't be too large extension fields. So we want to know what, just separate things based on where they live and which extension degree finite fields. And well, basically, all of these things are polynomials, rational maps, solutions to equations. So we can just make straightforward definitions where we say that it's defined over K if all the things that you need to write it down are defined over K. And here's a bit of notation. If you look at an elliptic curve over a finite field, or any field K, you can just look at the subset of the points that are defined over K. It turns out that this is actually a subgroup. So when you compose two things, you're never leaving the same field, which is very useful for computation. And yeah, right. So this shows up in many different places. It's not extremely important. So if you want to forget one of the math slides, forget that one. There's two more, but that's fine.
It went too fast anyway.
Am I?
But I will
Look at it again.
Comprehensibility failure.
Yeah, I've seen this stuff like a million times before, so you guys really have to interrupt me if I'm going too fast or something.
We're supposed to forget.
So this is actually important now. Big theorem. If you look at a group and a subgroup, you can quotient out the subgroup, right? In the abelian context, you can always quotient out and you get a group. Generally, you get cosets, blah, blah, stuff, whatever. Forget about it. Thing is, this also works for elliptic curves. If you take any finite subgroup, you can quotient out that subgroup. So it's basically a group theoretic quotient, but the remarkable thing is that this is still an elliptic curve. So somehow you get from group theory, you always get a quotient group, but this turns out to still be a subgroup of an elliptic curve group. And that's the thing here, right? And you also get an isogeny to this other curve that has that group as a ground. It's a bit like this homomorphism theorem for groups that I guess everybody has seen in their algebra course, except that you just plug in lots of elliptic curve specific things all over the place. The group homomorphism becomes an isogeny. The quotient group becomes a quotient variety. And, the reason why we care about this is because it allows us to choose isogenies by choosing subgroups. Right? So it's actually, if you just look at the equation for an isogeny, it's not at all obvious how to even find an isogeny. Like, how would you write it down? And this gives us at least an abstract way of identifying isogenies based on saying, I'm identifying subgroups. I'm just picking a finite subgroup, and that always determines an isogeny. And we shall see in a second that you can also compute this. Maybe now. Right. So Jacques Prelude in the 70s has found formulas that give you an explicit description of this isogeny that we know exists abstractly. And yeah, the complexity is in the size of G. So you want to make sure these groups are kind of small. But what this basically says is if you pick a small subgroup of an elliptic curve, you can always compute an isogeny to some other curve that you also determine along the way that has that subgroup as a curve. Right? And that's the primitive we're going to use to walk on the isogeny graph. Right? So every step will consist of choosing a subgroup, computing this isogeny, and then your new node that you're on after you made your step is the target curve of this isogeny. Right, I haven't actually mentioned this, but I should have. All of the all of the efficient existing isogeny-based crypto proposals use supersingular curves because that makes it very easy to control the group structure, and then you can make sure that these subgroups that we want to use actually are defined over small extensions, so it's all nice and efficient. Yeah, I also just said this. I'm somehow a bit ahead of my slides, but right. Another thing, don't remember exactly what this means. The important property is that by picking our prime of a specific form, like we're working over FP or some extension of FP, and if we pick P in a specific form, we can make sure that the group structure of the curves we're using is nice and useful for computing small extensions. And now slide 1 and 2, we're introducing nodes and edges, and now we're going to make the formal definition for what this graph looks like. And it's essentially what I said before, right? You just pick a bunch of degrees, prime degrees, usually. And then you just say, my nodes are still all the empty curves that are supersingular, that are somehow connected by these nice isogenies. And I'm going to look at all the isogenies that have these prime degrees, chosen in the set S, as edges. And then you make some identifications where you don't really care how to write down these equations specifically, so that's basically saying up to some notion of isomorphism. It depends a bit on the details. Right. So somehow the usual Diffie-Hellman picture is you have a group, and then your things you're operating are the group elements. And now we're basically going one level higher, where each thing that we're walking around on, or that we're using in our protocol, is a curve. And we're walking around by looking at maps between those curves. And we don't really, I mean, the points are still used as a means to compute these jumps in the graph, but they're not an essential part of the protocol. Okay, so examples. We're done with the formulas and all that now, so we can look at these nice pictures. Here's the first one. So as you can see, this is really nice. Huh? It's very structured, like it's very regular, it's symmetric. It has lots of nice beautiful properties. And this is what happens when Q, so 419 is a prime, as I guess everybody knows. So this is when you're looking over a prime finite field. It looks a bit like this. And if you go to a quadratic extension of that, or to the algebraic closure, which is sort of equivalent for reasons, it looks like this. So we could have a little audience poll. Who would use the first one for crypto? 3 people, okay. 4. The second? Okay, so similarly also like 3 hesitant. Okay. Right, the answer is both, obviously. And these are essentially the 2 main classes of existing protocols in isogeny-based crypto at the moment. And they're like they share the same underlying math, but they are quite different in applications. And somehow people always like to compare them, but they're not really. They're just different things. It's like comparing RSA and Diffie-Hellman because they both use modulo or something. Right. So CFAIL is actually something that Tanya and Chloe and I and Wouter Kastrik and Joost Rennes came up with. So I'm going to have a short little advertisement break. So first of all, you should remember to pronounce the C side because it's much nicer than CSIDH, which sounds not very cool. Also, remember this picture. This is really the thing you should remember about it. Yeah, what it is an efficient commutative action, blah, blah, blah. The main application that we proposed in the original paper is post-quantum Diffie-Hellman. So you get the 2 things that many other post-quantum schemes lack, namely the interactions between Alice and Bob are truly symmetric. It's like original Diffie-Hellman, everybody does the same stuff. There's no distinction between an initiator and a responder in the protocol. And the second thing is you can efficiently validate these Diffie-Hellman public keys, which is not true for other protocols. where, you know, if you have a malicious bot, they can trick Alice into revealing some secrets by crafting their public keys. Yeah, so this is really, in many ways, a drop-in replacement for normal traditional Diffie-Hellman, except that it's not broken by quantum computers. Yeah, so that's good. You know, this is fine. Nothing is, of course, we need to cut off the competition. Even though, you know, as I said, they're not really comparable, but still, whatever. So now we're doing SIDH, which is the thing we tried and failed to break. As you can see, the slide is less nice, so what does it tell us? Yeah, so I mentioned briefly on the C-side slide that this is computed with row prediction, and you get a sub-exponential attack. In a quantum setting, it scales worse than the classical attacks on RSA, so it's not really a problem, but you know, some people like to avoid this. And so SIDH uses the full isogeny graph where you don't restrict to the stuff over FP, but you actually look at all the supersingularity curves over that field and all the possible ways of connecting them. So that's the right chaotic graph. And that makes it seemingly resistant to the sub-exponential quantum attack. But, well, the graph looks much more chaotic now, right? It's not like this nice cycle symmetric thing where you have left and right paths everywhere and you can just walk around. It's nice. Which leads some people to say that it all bloody looks the same. I'm not going to say who it was. So you need to communicate some sort of extra information to make sure that the protocol still works. Right? So if you just start randomly walking and you compose these paths, there's little hope to end up on the same course. It's just, it really looks like a random graph. And there's theorems that say it makes it quickly as well. Okay, so the high-level overview of this protocol looks like this. It does look a bit like Diffie-Hellman. And it's color-coded, so red means this is stuff that Alice chooses in some way, blue means that's stuff that Bob chooses in some way. And if you don't remember this notation, well, it still doesn't work, yeah. The phi B and phi A are the isogenies from math slide number 4, I think.
You did it on the board.
Where, as a failure, but actually, laser
And then if
pointers.
people don't remember it, you can write it on the board. Or I can write it on the board if you like.
Yeah, you go, that's good. Yep.
I'll write on the board while you carry on.
Right. So things in this notation, A and B are subgroups, right? Use it at the curve.
I'm going to put it on the
Common to everybody. Now she's got all the attention.
And the camera is totally catching you there.
Yeah, I think that's a little hard for the cameras
Oh,
to
did I
see.
put that-
Do you mind putting it on the
Right.
whiteboard? Yeah.
Yeah, the action needs to be there.
Yeah, keep it to the right of the failures,
Tell us
perhaps.
the failures thing, 'cause it's not a failure.
It's not,
It's actually quite
right?
nice.
You can draw a line in between them to
Define
cordon it
essentially,
off.
or just say what essentially is.
What the notation is.
The E sub B.
Yeah, the phi P and the mod.
Right, okay.
Right. So the high-level protocol views, I'm just going to carry on and nobody can read this anyway because I'm standing in front of her. High-level protocol view, everybody agrees beforehand when you write the code on a starting curve E, and then when you run the protocol, both Alice and Bob each choose a secret subgroup A and B. So these are the little indices with the phi's and the stuff we mod out. And then what we want to do is, well, we communicate the target curves of these secretly chosen isogenies. And then in some way that's going to be determined, they both also can determine extra isogenies that make this thing a square instead of just 2 lines, I guess, half square. Right, and then by math and theory, the codomain curve at the very far right bottom will be the same. Right. Yeah, I just said this. They pick secret subgroups, and they compute these edges, and they communicate their end nodes. And now, in case you wonder what this has to do with the pictures of graphs, well, these subgroups are going to be chosen in a specific way such that computing these isogenies actually corresponds to walking little steps, one step at a time, n of them, where n is a small number, like, I don't know, a few hundred. And so the way you actually compute this is by hopping
We have
around.
a
in the
question,
specific-
sorry.
Yeah.
Just maybe I missed something, but aren't these just edges on the graph?
Well, Kinda. So the thing is, the subgroups are going to have very big order. They're going to be 2 to the n and 3 to the, that's like 2 to the few hundred and 3 to the few hundred. And if you were to compute this directly in the 2 to the few hundred isogeny graph, it would take forever. So the thing is, you decompose this into small 2 isogenies and 3 isogenies.
Each two isogeny is an edge. So
Yeah.
the map is like a lot of edges in a row on the graph.
Yeah. So the phi A here is a composition of many little steps on the 2 isogeny graph. Or 3, depending on. And right, so they communicate their end nodes, and then we would like to somehow make sure they can still complete this diagram, and that's the tricky part. So somehow Alice now needs to obtain this subgroup A prime of the curve that she hasn't started with, and has to make sure that this is actually the image of her own secret under Bob's secret, which is, as the color coding shows, pretty tricky because Bob only knows B and Alice only knows A, so how would you evaluate his secret on her secret without them disclosing them? But we're going to come to that next slide. Yeah, and then in the end, they, by construction, get the same shared secret. Actually, after I made this slide, I noticed that this is also the high-level protocol flow for C-side. So they do have something in common, except that the somehow part here becomes easier in C-side because there's canonical ways to choose these subgroups without really knowing the map that's in between them. Right.
Multi-party compensation.
Zero knowledge, something, buzzwords, yes, sure. If you can make that efficient, I don't know. So it seems pretty impossible for them to do this, right? Secret, they can't talk about it. So the solution is that, as you remember from math slide number 2, isogenies are group homomorphisms, right? So instead of making Bob evaluate his secret on Alice's secret in some way, Bob will just evaluate his secret on public basis points of, well, a subgroup that A is contained in. And then, because Alice chooses her own group in a linear combination, as a linear combination of this basis, she can also do the same kind of linear combination on the image points. And this is what this notation here says, right? So they just both agree on a fixed public basis of some subgroup, P and Q. And then Alice picks her subgroup as a special linear combination of these basis points, and Bob just publishes the image of those basis points under his secret. So he doesn't have to know what Alice's group is. And because phi B here is a group homomorphism, Alice can compute the image under Bob's secret by just taking the same linear combination of the image of the basis point. So this is really the core contribution of SIDH in some sense, that the observation that publishing these extra points makes it possible to still get this commutative diagram without multi-party computation. So based on what I've just said, here's another slide full of math to, I don't know, tell you all, whatever. So the SIDH construction chooses a prime of this specific form, 2 to the n, 3 to the m, because as you remember from math slide number 5, obviously, that means the group structure is such that all the points of order 2 to the n and 3 to the m are defined over fp squared, which is nice for computations, because it's small extensions, so you don't get big extensions. And then they agree on bases of the subgroups to make sure, well, yeah, Bob can publish this extra information and so on. And then they just do the thing I just explained, where Alice picks her subgroup in a special way, and Bob communicates the image of his own secret, of the public basis under his own secret, and yeah, in the end they just get the same curve up to some isomorphism, and we're done. Right, but the thing is, right. So if you're just, as a cryptanalyst, right, you now have extra information. It's not just 2 curves where it seems hard to find a connecting isogeny, but you also get some information about the secret because, well, Alice and Bob evaluate their own secrets on public information. So you know PA, you know QA, and you know phi B of these points. And it looks like there's some information contained in that might be exploitable. And yeah, we looked at many different ways of exploiting this information and also other information. And by now, it seems to me that all of this very obviously doesn't work. So I don't know, it felt a bit weird to write this down because it seems like it's all obvious by now. But still, we often talk to other people who are kind of new to this or have some ideas. And it turns out that many of these things are still thought about by people who could make better use of their time. So we thought we'd write this down, and even though it by now seems pretty trivial. All right, so there's a few initial observations about this. First of all, they don't only actually publish the information about 2 points. Right, so they publish the information, they publish the image of a basis of a subgroup, and that means you can actually just figure out which linear combination a given point is of that basis, and then recombine, just like what Bob does basically, recombine the images of the basis points in the same way, and then the bottom line is you can actually not only get the action of Bob's secret on 2 points, but on all of the points that they span, which is much more information. And that works because 3D theorem is very smooth, so you can efficiently find the right linear combination of the basis that gives you a specific point. So there's like a discrete log problem where if it's smooth, it's easy. Also, if you're, for kind of balanced parameters where 2 to the n is about the same size as 3 to the m, you can easily show that this information is actually enough to uniquely define the secret isogeny. So at least information theoretically, you're done, right? The secret is uniquely determined by all of this stuff, and now you just need to figure out how to compute it, which is the hard part. Right, so how to compute this? Isogenies are just rational maps, right? That's the definition. So we can actually look at stuff like polynomial interpolation, and then there's a variant of that works for rational maps. So you might think, I can just recover this map by plugging in all the known input-output pairs. The problem is these maps have exponential degree, so you can't even write down the answer. So that's kind of bad, right? If you can't even write down the answer, you also can't hope to efficiently compute it. So this is somewhat different from when you honestly run the protocol. You decompose this into small prime degree steps. You do lots of 2 isogenies. So you kind of hope to recover this map while at the same time decompose it into these smaller steps, because that's what makes it small. But if you just naively run polynomial rational function interpolation, you can just get a big exponential sized thing, and then you could start afterwards to decompose this as a composition, which is possible, but I mean it's exponential sized, so at that point you're already screwed. And there's, to my knowledge, no algorithm to do these 2 things at the same time, and it seems kind of tricky. Another idea is, what if we just gain a little bit of knowledge about how this secret isogeny acts on some other point that's not contained in the subgroup that we can already evaluate it on? And one crucial observation there is if Alice was to disclose the action of her secret on the torsion subgroup of her isogeny's degree, then she lost, because you can easily group theoretically compute what the kernel was, and when you have the kernel, you have the secret. But the problem is if you just look at group things, where you just treat the elliptic curve as a group and forget about all the geometry behind it, forget that it's a curve, just treat it as a group. Well, it just decomposes into the 2 co-prime torsion groups by some finite group classification. And this shows that if you just look at things that happen in groups generically without looking at the geometry of the curve, you just can't tell anything about it. And this, the annoying thing is that this somehow shows up in many different little disguises. Like there's different notation for the same thing, and in the end it all turns out to be just this problem. Like you can't see anything about something that's a co-prime subgroup. Yeah, so the short summary for this is quoting myself here. Very nice. If you just treat this as a generic group, there's no hope, and there's little you can actually efficiently do on elliptic curves that's not just group things, right? There's pairings, but they are also, in this context, you can just view them as linear maps or bilinear maps, and then you have the same thing. Anything could be a bilinear map. So it just looks like a generic group for most purposes, and in generic groups you can't do this kind of extrapolation thing. Yeah, so I was saying here maybe you could hope to learn something about another subgroup. Here the idea is it's very similar. To learn something about not 2 to the n, but maybe about 2 to the n plus 1, where you basically lift the known action to some higher, some bigger subgroup that contains the other subgroup. And the reason, don't be afraid of this, the reason why people think this could help is because there's a theorem that says, well, if you know how an isogeny acts on all the L to the n torsions, then it's uniquely defined. So the idea would basically be to just keep lifting this until you have enough information to uniquely determine the isogeny, and then you're done abstractly. The problem is that, again, all of this is super non-computational. It's completely unclear how to do any of this in computers. Also, if you just look at the group structure, there's L to the 4 ways to lift this action, right? You have L choices for each of the coordinates. It's a two-dimensional matrix. And there's just no way to tell which one's the right one, except that, you know, we know something. We know basically sort of that the determinant of this matrix must be co-prime to something, but this doesn't help a lot. It's just like a little bit of constraint that doesn't seem to lead anywhere. There's a variant of this idea where if you look at endomorphisms instead of general isogenies, so, you know, an isogeny from a curve to itself, this works a little better because you like an endomorphism has a nice notion of a characteristic polynomial. It has a determinant and a trace, and that makes more sense. But then it's still L squared choices for each of the lifting steps, which just explodes after a few steps. So there's not even then we know how to do this. Right. But this is something that people keep running into because this theorem is quoted in books on elliptic curves. And then they're like, oh, I now know something where I can recover the isogeny, but none of it is computational, so it doesn't lead anywhere. Right. So I just said all the group theory stuff doesn't really work. There's one approach that's actually kind of specific to elliptic curves, and that is, well, was introduced by Christophe Petit. And I'm going to try to give a short summary of that. So please ask questions if it's unclear. You know, it's not exactly easy. So I said at some point on math slide number 2 that the set of endomorphisms forms a ring, and the way that SIDH parameters are typically chosen, we actually know what this ring looks like. Like we can write down formulas for the maps that, or for a basis of this endomorphism ring, and we can efficiently compute it, and that's all nice. And now the approach that Petit was following is that if you, well, we know that the public curve of Alice on the right and the starting curve is connected by this secret isogeny, and we also know how to evaluate the secret isogeny on some subgroup of the elliptic curve. So we can just construct an endomorphism of this target curve by going back through the dual isogeny. That is kind of specific to elliptic curves. And then doing some endomorphism thing on the zero curve, and then going forward again. Right. And because we know how phi A acts on a specific subgroup of E8 and E0, we can actually evaluate this efficiently on that subgroup. And now the idea, the crucial idea in Petit's paper is if you find an endomorphism of this form, where you go back and forth, that has a specific degree that's divisible by the size of the subgroup that we can evaluate it on, you can recover that part of the map by looking at the known action that Alice has published. And then there's some remaining part that you have to just run brute force computation. So ideally here, you would just find an endomorphism of EA that's of this form, that's just of degree 3 to the m, and then you're done, because we just know what this endomorphism must be on the 3 to the m torsion, so we have the kernel, so we're done. Right, and then there's, so the problem here is, if you write down a formula for what the degree looks like, well, that's the formula, you can see 2 to the 2n's, and you can also see p's, which is about 2 to the 2n as well, roughly, for symmetric parameters. And looking at this slide, we wanted the degree of tau to be 3 to the m times something very small, because the small thing should be the stuff we need to brute force. So looking at this equation, most of the values, if you just plug in random A, B, C, and D, are very big. Right? They're going to be much, much bigger than 3 to the m. 3 to the m is about the size of 2 to the n. And here we have coefficients that are 2 to the 2n and 2 to the 4n. And so this is all very, very big very quickly. So basically, unless these parameters are very, very unbalanced, where Alice's degree is much smaller than Bob's degree, or vice versa, it's also metric, you can't really hope to find any element like this. It's just going to be much bigger very quickly, and then, well, you can, of course, find an endomorphism that has degree 3 to the m times r, but the r is going to be much, much bigger than the problem you started with, and then brute force r is just expensive. Right. So I think there's still some people hoping that this approach would somehow be improvable to actually break normal SIDH, but it doesn't seem that you can actually hope for this. That's just there could be improvements to break slightly less imbalanced parameters, but for the symmetric case, I don't think there's any hope. All right, so summing up my part of the presentation, then I'm handing over to Chloe. There seems to just be no way to extrapolate the known information to anything that's not already given. Sad face, you know. We can't really hope that Pitty's approach works for the actual SIDH protocol. Sad face. Also, life sucks. But, you know.
All right, on that note. So almost every one of my slides consists only of pictures. Except for the problem statement, which is the next thing. So everything Lorenz was saying was trying to use these extra points that are sort of looking a bit mysterious because they're not there in the original Diffie helmet, right? So you have, you've got, you're trying to find the secret isogeny, phi A, and you know also, you know phi A of PB and phi A of QB. Right? So Lorenz was trying to use these things.
You also tried that.
In Lorenz's part of the presentation, we were trying to use these things. But you can also just sort of try and reconstruct this isogeny in some other way that doesn't use these extra points. And so we also thought about lots of ways that don't achieve that. Right, so this is the fundamental problem. Given supersingular elliptic curves, E and E prime over fp squared, that are L to the n isogynous, so L is 2 or 3, compute an isogeny between them. Right, it doesn't necessarily have to be the same one. If you compute any isogeny, so any map that's also root homomorphism and stuff, then you're done. Okay, so what are lots of ways that you can't do this? Here's an example of 2 curves. So don't worry what these specific formulas are, but these are 2 elliptic curves defined over F431, so actually over FP in this case, not FP squared, just because this is trying to make it a bit more of a simple example. And these are isogynous, right? So there is an isogeny between them of degree 4. So you can think of that either as 1 isogeny of degree 4 or 2 isogenies of degree 2 that you can compose. And we want to try and compute an isogeny. It doesn't have to be that one, but this is quite small, so probably this will work out if we compute that one. And the kernel, right, this is a degree 4 isogeny, so the kernel has size 4, so it contains 4 points, 4 solutions to that, well, 3 solutions to that equation and the point at infinity. Okay, so on one of Lorenz's math slides, I don't know the numbers by heart, he told you that the kernel of this map actually tells you what the map will be itself, right? So you can basically do some sort of interpolation type thing. If you have the points, then you can find the map that defines, you can find the rational map that gives the isogeny here. So if we can find the right kernel, then we're done. So here's one solution. So there are 9 points of order 4. Just take my word for it for the moment. And you can try them all and see when you get the right answer. Right, so you take all the, sorry, not 9 points of order 4, there's 9 subgroups of order 4. And each one of those, there's more than one thing that generates that subgroup, but you take all the 9 different possible isogenies of degree 4 going from this curve, and then you see which one lands on E prime. Okay, so then there's a slightly better thing you can do. Right, so remember I said you can either take a degree 4 isogeny, or you can take 2 degree 2 isogenies. So you can split this up, and you can start from both sides. Right, so you start from E, and say I find all the degree 2 isogenies, there's 3 of those. And you start from E prime, and you also find all the degree 3 isogenies. Degree 2 isogenies, and there's 3 of those. And so then you only actually have to compute 6 things, and you just check where they collide. Yeah, so if you look at the graphs, then you have, ooh, this doesn't work.
Yeah, but you can't write it because it doesn't work. So.
Okay. So the solution B is like I take my 3 different 2 isogenies from E, I take my 3 different 2 isogenies from E prime, and there will be 1 collision. Yeah? And then I can construct my map from E to E prime by saying, well, it must have gone through this node here, right? This elliptic curve here. Okay, so as this picture shows you, this is a very, very small instance of a method called meet in the middle. So if you think of the graph approach, you know, where Lorenz is walking around Manhattan and I'm walking around Manhattan, this is when we randomly walk until we bump into each other in Central Park, or whatever. Yeah. And in general, if you take a bigger thing where your things are defined over fp squared and you've got some very large prime of 512 bits or something, then the complexity of this is roughly p to the 1/4. So this is the complexity that the designers of SIDH or SIDH, which is the NIST version, are relying on. So if we can do better than this, then we win. Spoiler alert, we're not going to win. But this is the do better than p to the 1/4. Okay, so Lorenz showed you this in this commercial break. We had Beauty and the Beast, right? So the Beast was this crazy-looking graph, and the Beauty, which of course in my non-biased approach is much more beautiful, was this kind of circle thing. These compositions of circles that look like a spirograph. Yeah? And where did that difference come from? Well, here we've got p squared, and the cycle thing was over p. So if you just take only the nodes, which correspond to equations with coefficients in fp rather than fp squared, then we get a simpler graph. It will look beautiful in a minute, I promise. Okay. So this is one. So we can already take away a lot of the noise and say, okay, what happens if we can somehow exploit this subgraph, right? Because this is much, much simpler than this crazy, messy ball of string on the left. Okay, so So remember, with our example, we had they are 2 nodes that were in this graph. Maybe I can't remember actually if they are, but so that would be 2 orange steps, right? That's a 4 isogeny, so 2 isogenies. But we could also find a path of 3 isogenies, right? And that might be much longer, it might be much harder to find. So let's just then strip away even more and just take the FP graph of 3 isogenies, which is this one. And here I've got this little thing that's appeared that says nodes up to FP bar isomorphism. So if you're familiar with elliptic curves, then you can think of this as being J invariance. If you're not, wipe your memory, I didn't just say that. But basically, if 2 of our curves are isomorphic over the algebraic closure, then we just collapse it into 1 node. But you don't have to do that, because actually when we're talking about things over FP, that doesn't make so much sense. What you can also do is take your nodes only up to isomorphism over FP. And as you can see, this makes a lot more sense. Okay, so then you get this much more understandable graph where you think, okay, maybe now I can detect in our very simple, small example, right, we can just take our 2 curves and we can just go, okay, I can see the path, there it is, I can compute it, yeah? So in a bigger example, where you've got 512-bit primes, this might be still sort of a huge amount of work, but there is the attack that Lorenz mentioned on Seaside would also apply to this subgraph here, this FP subgraph. And so that's Kuperberg's sub-exponential quantum algorithm, which computes a hidden shift. And so the concept of a hidden shift looks quite natural in this cycle, because it's like a shift around the cycle, and you're trying to detect how far you went. So the shift is hidden how far around the cycle it is. And that's the hidden shift that Kuperberg's algorithm finds. And this is sub-exponential complexity, so if we can find this FP subgraph, then we're better than p to the 1/4, and that's all we care about. Also, then SIDH would be as insecure as Seaside, so that's all we care about personally. Okay, so what about this? So if we can exploit this subgraph, what do we need to do? We need to find a path in this big crazy graph from Alice's secret, or Bob's secret, or whatever, to the nearest curve that's inside this FP subgraph. Okay, so the nearest, you see we've lost some nodes on the left here, so we need to find the nearest, a path to get to one of these nodes that's on the left still. Okay, how much does that cost? P to the 1/2. So this is an even worse way of breaking SIDH than the most generic attack. So this is actually quite an epic fate, this particular approach. Good. So that's one way to not break SIDH with the pure uncertainty problem. So you might ask, okay, there's this really nice graph sitting inside there that's somehow hidden. Is there another way to exploit like nice subgraphs? Well, yes. Well, no. I mean, there are other nice subgraphs. There's no way to exploit them that we found. Okay. So here is a 3D picture, as you can see. So the thing at the bottom, that's the thing we had before where we've taken away the orange edges. So now we're just looking at the 3 isogenies. And you can do this like crazy algebraic geometry stuff, so elliptic curves are one-dimensional things. So you can increase the dimension by 1 and decrease the degree of the extension by 1. So you can sort of choose what you want to do in some way. So you take your one-dimensional curves over FP squared, and you get 2-dimensional surfaces, varieties, words, don't worry about them, over FP. And because they're over FP, if you take this FP subgraph like we did before, then you get exactly the same picture we had for elliptic curves. And then you think, woohoo, we can do Kuperberg's algorithm. Well, you can. But let's see what goes wrong with that. Right, so the associated graph, so that's the cycles at the top of 2-dimensional objects. You're probably going to get about square root p cycles, and each length is going to have square root p. Don't worry about those words. That's only if you happen to be an algebraic geometer. Okay. If your 2 elliptic curves are in the same cycle, right, then they're isogynous. That means there's a path between them. And Kuperberg's algorithm can find isogeny in sub-exponential time. But as you've probably already spotted the flaw in this argument, the probability of being in the same cycle is 1 over square root of p. So this gives you like a really, really bad chance of breaking it in sub-exponential time. Or you can do it square root p times, and then again you have something worse than meet in the middle. So this is another approach that doesn't work. Okay, so then there's one more thing that doesn't work. Well, there's probably lots more things that don't work. There's one more thing that we thought of that doesn't work. So if you're looking at this picture where we had this crazy graph on the bottom and the cycles on the top, what you're essentially doing is you're rephrasing your elliptic curves as some other thing. And if this means anything to you, you can think of that as a kind of equivalence of categories. So there's another category where things are easy, and that's elliptic curves defined over the complex numbers. Right, so if you just look at the top here, so you've got elliptic curves where so polynomials with coefficients in C. And they've got a special endomorphism ring, don't worry about that, but this is just what makes it work. And if you've got 2 polynomials with coefficients in C, finding a map between them is actually just linear algebra that's super fast and really easy, which is awesome. So that's why computing isogenies there is easy. And there's a really nice equivalence of categories with non-supersingular curves, which is exactly the ones that we are not interested in, defined over a finite field with the same endomorphism ring. And so these are the things that we are interested, like almost the things we're interested in for cryptography. Computing isogenies, but computing isogenies there is much harder. So we thought, what if there's something similar that we can exploit for supersingular curves? So there is something similar. Okay. So again, we've got elliptic curves defined over C. The condition has changed slightly, but whatever. And underneath, we have the supersingular elliptic curves that we care about, defined over FQ. And we just have to find a non-scalar endomorphism. So remember, Lorenz told you there's scalar multiplication always, that you always have in every group, or exponentiation if you prefer, whatever. composing a group element with itself m times. So everything except for that would be awesome. Except for everything except for that is ridiculously hard to compute. And even if you could, computing with an up and down arrow is really slow. Finding the non-scalar endomorphism is hard. And if you could, there would be way easier ways to break SIDH, which have already been figured out by smart people. So this approach is overcomplicated and uninteresting. Thank you very much.
Do we have any questions?
Oh, yeah.
So, I think inside the first version, at least, it fixed the initial curve.
Yeah, E0.
Does any of our approach, your approaches that you guys have studied, improve in any way when you get initial curve?
Yeah, so everything that relies on constructing endomorphisms relies on knowing that the initial curve is E0. So that's like, Petit's attack, which with the unbalanced parameters, you need that. But it's also open problem how to construct a supersingular curve. So you apart from just walking from the initial curve, and then you've got like security backdoor problems. So you might as well just start with E0 and, I don't know, if you can solve the problem of, the best ideas to solve the problem of find a random supersingular curve would actually show you how to construct endomorphisms, which would then break SIDH. So yeah, it's all kind of related.
But in practice, it's not that much of a problem, right? I mean, there's a variant of this where...
Well, it depends if someone manages to break it.
Right.
Not for us, because we can't break it.
Right, so the fixed E0 makes it easier for cryptanalysis sometimes, but then again, we can't break it anyway. But if that's actually a problem, you can easily get around it by just randomizing the starting curve every time by a trusted party, so one of us above. So it's not that bad.
Yeah?
For the story with few cycles, can you do some meet in the middle attack between the cycles to try to get that P to 1/4 and the we can still solve it in P to 1/4 easy operations. Like try to re-randomize PC of that second.
We thought about something along those lines, and you can, but it ends up being as bad as generic meet in the middle. So,
Is that it? Okay, let's thank our speakers again.